So the question I ended with on Wednesday, how do I find those critical values? How do I know whether or not, once I get my data and my test, whether or not I should keep or reject my null hypothesis? It depends on what we're testing, because what we're really building is the same sort of idea we built for confidence interval. So it depends on whether we're testing a mean or a proportion. And if we're testing a mean, whether or not we know anything about the population in terms of its standard deviation. But the advantage to this is that the decision-making process for what I am doing is exactly the same as it was confidence intervals. So option one, if I know the variance of the population standard deviation, and I want to test a mean, well, then I can say, oh, if I know a population standard deviation, I was doing a confidence interval, what table would I use to figure out how wide the confidence interval should be?
Like one of the C tables.
My normal distribution, my C table. And since what we are doing with our testing is finding whether or not we're inside or outside our confidence interval, we're going to use the exact same thing. And if I'm using a normal distribution, then my test idea is a z-score. What's the formula for calculating a z-value? Right, the value minus the mean divided by the standard deviation. But I'm testing my average against the predicted average, right? We had this null hypothesis. My null hypothesis is that my mean is either equal to this number or less than this number or bigger than this number, whether I'm doing a left tail, a right tail, a two tail, that tells me, but I have this benchmark score. Remember the example I was doing on Friday? I said, oh, the average should be 4. That's our mean 0. I gather my data. And I figure out my average. That's my sample mean. I want to test is this inside the confidence interval? The z-score is the value I computed minus the expected value divided by the standard deviation, except the standard deviation for this thing is not the same as the standard deviation for the population. I don't just want to put sigma on the bottom down there, because that's the entire population, not when I'm sampling. How did we change this for confidence interval? What did we use instead of the standard deviation? We even gave it a name in the chapter you just gave me.
Like the right side of the equation, but without z for like the confidence interval. So it'd be like sigma over square root of n.
Exactly. And we called that the standard error for our mean. We called it sigma x bar rather than just sigma x, sigma. Instead of being the standard deviation, it's divided by the square root of n. So our sample size plays a factor here. This is my test number. My confidence interval, I had to multiply that by the width of my interval. The width of my interval depended on my confidence level. So in order to figure out what to compare this z with, that's my critical value. And that's going to depend on my alpha, my choice of error, my margins, the one I say, oh, how confident do I want to be? Okay. How confident I want to be comes down to this table. Comes down to my C table, my normal distribution. So let's make a decision. If I'm doing a one-tail test, I need all of alpha to be in one tail. Here are some alpha values. If I say my alpha is 10%, then I'm looking at a 90% confidence. If I was doing a left tail only, I want to know what the 10% mark was. I'm going to call that the left tail critical Z. I'll write it Z crit. But I don't just pull this number out of thin air. I go here. And I say in the cumulative distribution function, table C2, what Z value gives me an area of 10%. So I start looking for 0.1 on my table. 0.01, 0.05, 07. Oh, here we go. 08, 10. Let me back up a little. 1003. So it'll be between these two, right? So that's harder to see over there. 1.2 between these two. Which one is this column? Go all the way back up to the top. And I see that's 8. So negative 1.28 is what I would get here. Now I can also use the inverse normal in Excel. And I could say, hey, jump to Excel. Let me open up a new tab. And I could say, give me the inverse. Okay, where's normal? Normal inverse is all the way at the bottom. Norm.inv. What's my probability? My probability is 0.10. My mean is 0. My standard deviation is 1. Negative 1.28. There's the same value. I can go to my graphing calculator. Same way. Because there's a normal inverse in the graphing calculators. Under the distribution, there's the inverse normal. 0.1, negative 1.28. The textbook actually wrote negative 1.282 because it rounded that off. I don't care. If you use the table and you write 1.28, I'm perfectly fine with that. Wait a minute. By symmetry. Remember, my picture for my normal distribution is the same on the left as it is on the right. What's the right tail critical Z? Positive 1.28. So the only question is what goes here in the middle when I do two tail? Wait a minute. If I'm doing a two tail, I'm not looking for 0.1 anymore. Even though that number is 0.1, look at our picture. Our picture for the two tail has the area split in half, so I'm looking for 0.05. Wait a minute. 0.05 on each end means 90% in the middle. That's the number that goes with our 90% confidence interval. What number went with our 90% confidence interval? I wrote that one down last week. 1.645. And notice that it's on both sides. So I need two critical values, a positive one and a negative one, but they're the same number just on each side. Oh, wait a minute. That's the number for 0.05, isn't it? right? 0.05 on the left, 0.05 on the right, which means that tells me that when I want a 95% security, this number will be negative 1.645, and this number will be positive 1.645. I got the next line in the table for free. What number goes in the middle? What goes with a 95% confidence interval? Bingo. Which, if you look carefully at our cumulative distribution table, if we're got 5%, we split it in half, that's 0.025, right? Half of 5 is 2.5. Here's my table. See the box around 0.025? 1.901, 2, 3, 4, 5, 6. That's the one we use the most often. That's why it gets circled. Here. Again, I don't know these numbers by memory. I have no idea what they are off the top of my head. But if I want alpha to be 0.01, I know where to go to look for that. Double zeros, double zeros, doubles. Aha, here we are, 0.1. Bing. Negative 2.32. That's probably closer to 2.33. And it turns out to be 2.326. If I use any of my calculation devices. In the middle, I'm going to have to look for 0.05. Sorry, 0.005. Go back and start looking for 0.005. .003, 004. All right, here we are, 005. Negative 2.5 between 7 and 8. So I have critical values. And now I can do my decision. I know, depending on what kind of test I'm doing, if I'm doing a left tail, I should reject if my calculated Z is in the rejection zone. If I'm doing a right tail, if I'm in the rejection zone, if it's too big, if I'm in a two tail, I could either be too small or too big. I just have to be outside. So my decision rule, whether or not I reject my null hypothesis, depends on whether or not my calculated number is in the shaded area. If my negative number is more negative than my critical value, then the absolute value will be more positive than the absolute value of the positive critical value. In all three cases, this is the way to make my decision. Okay. Let's take a look at an actual problem and see if we can walk through how we get this idea put together. Questions on the abstract version? Page 332, problem number 17. Green Beam Limited claims its compact fluorescent bulbs have no more than 3.5 milligrams of mercury. Mercury is toxic. If you break a compact fluorescent light bulb, technically, if it lands on the carpet, you're supposed to cut up that square of carpet and throw that out by calling it hazmat. You can't even put it in your garbage. Don't buy CFLs, they suck. Buy LEDs. A sample of 25 bulbs shows a mean of 3.59. Oh crap. 3.59 is bigger than 3.5. Is Green Beam lying to us? Or did I just get a weird sample? Write the hypothesis for a right-tailed test using Green Beam's claim as the null. A right-tail test. Okay. In my head, the only way to keep it straight is to think of the picture. Right tail means it's unusual if it's way up here on the right. So on my null hypothesis, everything is fine. I got a weird sample. I'm going to claim that it's less than is good. And alternate, it's too big, is bad. A right tail test. I did a sample of 25 bulbs. And my sample calculation was 3.59. I want to know what the null hypothesis is. I want to know what the alternate hypothesis is. If we think it's too high, that's my alternate. That's the thing that's unlikely that I want to show. Hey, this was really bad. So I'm going to say our alternate hypothesis is that our average is really too big. And our null hypothesis is that we're fine. A right tail, too big. That's alternate. Okay. Now I have to ask, did my sample fall into this category or this category? And they're very specific here. Assuming a known standard deviation of 0.18. So they're telling me a standard deviation for the population. What's my calculated z-value? I just kept writing z. I'm actually going to write z sub calc. And then I have the calculated one and the critical one. We haven't looked up the critical one yet. I just wanted the calculated one first. What's my z-score? formulaically, I take my test value, the one I computed, subtract the expected value, divide by my standard error. Do I know all four of those numbers? I have my calculated value, I have the expected value, I have the number of samples n, I have the process standard deviation. What do you get? Austin? Say again? I think you forgot to set parentheses. In order to do this calculation, 3.59 minus 3.5.09, that's the top, divide by parentheses, 0.18 divided by square root of 25. A much smaller value. Can't forget that. Sometimes it helps to do that calculation first. I always think of just putting parentheses around the bottom when the bottom's not one single thing. So I have my statistic. And now I ask, how much of a pain in the ass is the Environmental Protection Agency? How strict is their test? Are they going to say, well, we want to be 99% sure, we want to be 95% sure, we want to be 90% sure? How big is their confidence interval? In this case, the problem in the textbook says at the 1% significance level, determine whether or not green beam is telling the truth. Well, that's our significance level, that's alpha. Well, if I know that, what's Z critical? What's our critical value? Careful. Positive or negative? Exactly. That's the one we get off our table. If we use the one that was written in the book, 2.326, it's still very close to that. If you use the one off your calculator, you'll get more decimals. I don't care. Wait a minute. Now you can make your decision. Is the statement green beam claim that the average is 3.5 milligrams of mercury correct or not? I wrote at the top of this page, what's our decision rule? Reject if
Because the calculated Z score was greater than critical score.
aha. Is the calculated one bigger?
Yeah.
Rejected. Our evidence does not support the claim they made. I'm not going to go up to the green people and say, you're lying. I'm going to go up and I'm going to say, hey, our testing found that you are out of compliance with environmental regulations. Here's your fine. If I'm from the EPA, maybe I'm from the advertising companies. And the advertisers are like, wait a minute. You said 3.5. This is 3.59. We're going to get sued. Don't do this to us. My sample tells me I don't have enough evidence to say you're right. My evidence actually says you're probably wrong. Notice that word probably. Why did I use the word probably?
Could this be like a weird sample?
I'm using a normal probability distribution. I don't have hard, concrete guarantees. I have a probability. The chance that this was unlikely was 1%. 99% of the time, this isn't by chance. This is and in a sense, that's really what this significance measures. It measures how likely was this to happen randomly. Only 1% of the time this would happen randomly. Means I'm pretty sure your average isn't 3.5. It's bigger than that. It might even be bigger than 3.59. I might have gotten a low sample, but I'm pretty sure it's bigger than 3.5. Questions? I like this method for figuring out whether to reject or keep my null hypothesis. There is another method that I can use that doesn't require me to know a critical value. Throw this out. What if instead of having a critical value, I used the normal distribution table the regular way? Z is 2.5. Go to your table and calculate the area that goes with 2.5. And what I'm going to ask you is, what is the probability? What is the probability that Z is bigger than 2.5? What's the chance? Well, bigger than or equal to. What's the chance we got that number? How do I find this information?
Whatever you did.
So if I go to the table and I do the CDF, table 2, I'm not going to look for negative numbers, I'm going to look for positive numbers, but that's going to give me the left side of the picture. And I want the right tail. So the right tail comes from 1 minus this. That would be 1 minus the probability that Z is less than 2.5. And that I can use my CDF for. So what do I get when I get plug in 2.50? And if I subtract that from 1, I get. So there is a 0.0062 chance this happened randomly. Right? But what was my cutoff threshold? My significance level, alpha, was 1%. Is this number bigger or smaller than 1%? I said I want a 1% level that this is wrong. So I just need you to clear 1%. And you didn't. I'm going to give this a name. Well, this is a probability. I'm going to call this a p-value. And we reject our null hypothesis when the p-value is smaller than alpha for a one-tail test. But in a two-tail test, I got to check the probability on both sides, right? So I'll compute one p-value, but it'll only be for one side. So I'll have to multiply by 2. So in our example, there was a 0.6% chance that your sample was just weird. But I said, you need to be at 1%. We didn't make it. So here in the middle of page 329, we have this, what is a p-value idea? The p-value is the probability that our sample agreed with our null hypothesis. The bigger my p-value, the more likely we agree. The probability is good. The smaller my p-value, the less likely we agree. And when my p-value is too small, I'm going to reject my null hypothesis. It's very unlikely that this evidence supports what I want to know. Or what I'm claiming. Questions? Try another one. Page 333, problem number 23. An airline serves bottles of Galena spring water that are supposed to contain 10 ounces on average. The filling process is normally distributed and has a standard deviation of 0.07 ounces. 12 randomly selected bottles. Here are their weights in ounces. It says in the problem, set up a two-tailed decision rule to detect quality control violations using the 5% level of significance. Alpha is 0.05, two-tail. Before I do any calculation at all, I need to know what I'm testing. I'm testing a hypothesis. I'm testing my null hypothesis. What is my null hypothesis?
Know that like that the average is 10.
And then the alternate would be
Not equal to.
correct. Either it's 10 or it isn't, because it's two-tailed. Great. Problem, they didn't actually give me the mean. They didn't give me the standard deviation. Wait, no, they gave me the process standard deviation, didn't they? Yeah, they said the process standard deviation was 0.07. So let me make a note of that up here, because if I don't write it down, I will be stupid and forget it. So what I need is the average. They gave me the data though, right? They actually gave me all the numbers. So I can simply grab that data. That's the wrong one. Stop. I want to share. Wait, I wanted to share that one. Oh, it brings up the other one because that's not the one I'm using. Don't save. There it is. There's my data. Bottles of Galena spring water, actual fill volumes by ounces. How do I get the information I want? What do I need from this data? I probably want more decimal places. So let me go in here and I will change the format, Command 1, and I'll tell it to use more decimal places. I'm going to go with at least 3 decimal places. So I'll go with 0.015, sorry, 3 significant digits. I'll go 0.0158. So the average 10.0158. I'll write that down. Hey, wait a minute. I could do the Z calculation here, couldn't I? I don't actually have to do this calculation by hand. There, that's the average for my data. So let's actually do the Z-score. To do the Z, I take this number and do what? My formula for Z. Wait, hang on. Subtract the expected. What was our expected? Minus 10. And then divide by parentheses. Square root. SQR, there's square root, SQRT, 12. Notice how I put that entire thing in parentheses? The 0.07 over the square root of 12 is in parentheses, so it divides by the whole thing. Austin, that'll prevent my calculator. Yeah. That's my Z value. And I didn't have to round off at all. Okay. Before I go any further, it's a two-tailed test. We have two options on how to do this. We can do the Z critical, or we can do the p-value. We're going to do both. How do I get the Z critical?
Like, for the alpha value.
Almost. If I do the inverse norm for
Half
the
the alpha value.
half the alpha value because it's two-tailed. So I'm going to do the normal inverse parentheses, the probability. Alpha was 0.05, so 0.025, comma 0, comma 1. Or you could use norm dot S dot inverse because the S means standard. Why is that negative? There is a reason, I promise. Negative.
Yeah, because we only put in, what, 0.025, so it's on like the left side.
It's on the left. So I need that one and I need the other one, right? The other one would be positive of the same number. But that's 1.96, isn't it? Plus or minus, yeah, alpha was 0.05, 95%, 1.96. It's the same number. If I didn't remember it, I at least found it. Hey, wait a minute. My Z value, is it in the rejection zone? I either need it to be bigger than 1.96 on the right or smaller than negative 1.96 on the left, and it's 0.78. Don't reject. There's one other way I could have done the p-value, right? The p-value would have actually asked for the normal distribution for that Z. What's the p-value? Well, that's the normal probability equals norm dot dist parentheses this Z value. The mean is 0, the standard deviation is 1. And I want the cumulative. Using the CDF. Is that smaller than 0.05? There you go. Oh, I forgot I need to multiply by 2, don't I? I forgot to subtract the 1. I did 2 different wrong things. Wait a minute here. It's 1 minus this. 1 minus that. There we go. But that's only half of it because it's a two-tailed test. I need to multiply by 2. Is that smaller than 5%? 0.05. Is that smaller than 0.05? 0.4 is a lot bigger than 0.05. That's 43%. Not 5%. That's too big. Remember, we reject when P is small, not big. That's the difficult thing to remember. If I'm looking at Z's, I reject when the Z is too big or too far out. When I'm looking at P's, I reject when it's too small. There are several more examples. This is on our Canvas page. I have all of my other calculations over here. There we go. So you can play with that one as well. I will see you all on Monday. Have a wonderful weekend.